Okay, hello guys, Mr. Lau here again. So today I'm going to go through tutorial 4, which is fluid in motion. Okay, basically this chapter deals with your continuity equation, your Bernoulli equation, and of course your modified Bernoulli equation that contains the head loss. Okay, first question. We have a 20 mm diameter pipe which forks, one branch being 10 mm in diameter and the other is 15 mm in diameter. If the velocity in the 10 mm diameter is 0.3 and that of 15 mm is 0.6, calculate the velocity and the rate of flow in the 20 mm diameter pipe. Okay, so it will be good if you can draw a diagram to actually help us in the visualization. So basically we have the main branch, then it actually forks out into a 10 mm and also forks out into a 15 mm. So this is your 20, this is your 10, and this is your 15. Okay, can? So I'll label here as your 1, 2, and 3. Okay, so we are asked to calculate the velocity and the rate of flow in the 20 mm diameter pipe, okay, which is this one. So what we are going to do today is to apply your continuity equation, okay, whereby the flow rate in 1 is equals to the flow rate in 2 plus the flow rate in 3. Okay, can? So today for the flow rate in 1, it will be given by A1C1, flow rate in 2 will be A2C2, flow rate in 3 will be A3C3. So in terms of the area, okay, is the area of the pipe, so it will be given by pi over 4 d square. So d today I'll use 20 mm, okay, times your C1, which is your unknown. Okay, next your A2 will be also pi over 4 10 square C2. C2 in this case is given to be 0.3 meter per second. So 0.3 meter per second plus pi over 4 15 square, and C3 is given by 0.6. So it's 0.6 meter per second. Okay, and you realize that I did not change the units for diameter, okay, because all are in mm, so you will cancel off. Alright. Okay, so if you work this out, your C1 will give you 0.4125 meter per second. Okay, can? So we are also asked to find the discharge or the flow rate in the 20 mm pipe. So in this case, okay, it will be Q1, which is equals to A1C1. Okay, so try to compute this in SI unit. So A1C1 will be pi over 4 times 20 over 1000 square times 0.4125. So this will give us your 1.296 meter cube per second. Okay, so this is your discharge at 1, or your flow rate at 1. Okay, that's it for question number 1. Okay, next we have question number 2. We have a 300 meter long pipe, okay, which tapers from 1.2 meter diameter at A to 0.6 at B, and is sloped downwards at 1 in 100. Okay, the pressure at A is 69 kilonewton per meter square, and the rate of flow is 5.5 meter cube per minute. Neglect frictional loss, find the pressure at B. Okay, so these are the information given to us. Okay, if you want, we can label it. So today the diameter here is 1.2 meters. The diameter here is 0.6 meters. Okay, how about the total length? The total length of this tapered pipe, right? Okay, today is actually 300 meters. So we need to know the height difference between A and B. So how do we know the height difference? We are given that the slope is, for every 100 there is a 1 meter drop in height. So for every 100 meters, there is a 1 meter drop. Correct? So meaning to say, if there's a 300 meters distance, that theoretically based on this ratio, okay, should be 3 meters drop. So the height difference between point A and point B is actually 3 meters. Okay, so that's the first thing that we can consider. So the next thing that we want to consider, because ultimately we want to apply the Bernoulli equation. Okay, other than the height difference between A and B, what we also need is the velocity at A and the velocity at B. Okay, so how do we get the velocity at A and B? So today, okay, we are given that the flow rate, okay, Q is actually 5.5 meter cube per minute. Okay, we change this into meter cube per second. So this is 5.5, okay, meter cube over, previously it was 1 minute, right? 1 minute was 60 seconds. So 5.5 divided by 60, this will give you your 0.09167 meter cube per second. Okay, so the flow rate here is this. Okay, so today the flow rate is the same, which is your A1C1. Okay, for this point. So today 0.09167 is equals to the area at A, okay, which is pi over 4 d square, which is 1.2 square C1 which is CA lah. Okay, I'll label it as CA. So CA here, if you compute this, will give you 0.081 meter per second. Okay, same thing, we also need to calculate your CB. So same concept, 0.09167 is equals to A2, which is pi over 4 times 0.6 square times CB. Okay, so if you calculate your CB, this will give you your 0.3242. Okay, so you have our velocity for A and also for B. So now I'm going to apply your Bernoulli equation. So apply Bernoulli between A and B. Okay, between A and B. So write down the formula first. It will be PA over rho G plus CA square over rho 2G plus ZA is equals to PB over rho G plus CB square over 2G plus ZB. Okay, so today the unknown is PB. We need to find PB. Okay, so the rest by right we should have. Okay, so let me put in the rest of the values. So today, what is my PA? My PA was given to be 69 kilonewton per meter square, right? Okay, so I will put in. So today this will be 69 times 1000 over rho G. So rho G in this case I will keep it first. Okay, can, plus your CA square. CA square is 0.081 square over 2G plus ZA. So ZA, we do not have the absolute value, but we know that the height difference between A and B, okay, the height difference between A and B is actually 3 meters, the vertical height. Okay, so A is higher than B. So what we can do is actually to bring this ZB across to give you ZA minus ZB. Okay, so we leave it there first. PB we do not know. Okay, and your CB square, which is 0.3242 square over 2G. Okay, so this is what we have so far. Okay, so we can shift everything across to one side. Okay, so PB over rho G is my unknown. So the remaining terms will be 69,000 divided by rho G plus 0.081 square over 2G. ZA minus ZB, as I say, is 3 meters. Okay, minus away 0.3242 square over 2G. Okay, can. So your PB, okay, eventually you can bring the rho G across. So rho G times your 69123 over rho g plus 0.081 square over 2g plus 3 minus 0.3242 square over 2g. Okay, so this is what I have eventually. Let me get another piece of paper. Okay, so we need to sub in the values lah. So what is the rho? Today this is water, right? Okay, so rho will be 1000. Okay, so from here, okay, this will be equals to 1000 times 9.81 times 69000 over 1000 times 9.81 plus 0.081 square over 2 times 9.81, okay, plus 3 minus 0.3242 square over 2 times 9.81. Okay, so if you calculate this whole thing, okay, you should get 98.3 times 10 to the power 3 Newton per meter square, and this converts into 98.3 kilo Newton per meter square. Okay, so this will be the final pressure at B. Okay, can. So if there's no question, we'll move on to question number 3. Okay, question number 3. Okay, what we have here is a reservoir, okay, which is discharged into the atmosphere through a 50 meters long pipe and 100 mm in diameter. Okay, so the length here is 50 meters, the diameter here is 100 mm. Okay, so the outlet of the pipe is 30 meters below the surface. The head loss in the pipe is given by this formula, 0.5 c square over 2g, okay, per meters. So where c is the velocity of the flow in the pipe, calculate the velocity of the flow in the pipe. Okay, so for A, concept is very simple. What we need to do is to apply the modified Bernoulli equation. So where do we apply into? Since the velocity is the unknown, so we try to apply it to two places where we know the pressure. So I'll choose here 1 and 2 because all these are open. Open means it's atmospheric. Okay, so we will apply the modified Bernoulli equation between 1 and 2. Okay, can. So write down the formula: P1 over rho g plus C1 square over 2g plus Z1 is equals to P2 over rho g plus C2 square over 2g plus Z2 plus your H loss. So the head loss is due to the flow in the pipe. Okay, so between 1 and 2, okay, both are the same, atmospheric pressure, correct? 1 and 2 are both atmospheric pressure, so it will cancel off. Straight away we can cancel. Okay, next, C1, the velocity at 1. The velocity at 1, this is the surface, is stagnant, it's not moving, so this will be 0. Okay, also, because this is the datum, that means the reference point, okay, we can treat this reference point as 0. Okay, so that is the remaining terms that we have. Okay, so 0 is equals to C2 square over 2g plus Z2. So what is Z2? Z2 is the height from the reference point or the datum. So if this is the reference, 2 is 30 meters below, so it will be negative 30. Okay, plus your losses will be half times C square over 2g. In this case is per meters, right? Okay, so we need to remember to multiply by the total length of this pipe, which is 50 meters. Okay, can. So this C2 and this C will be the same because the pipe is the same cross-sectional area. Okay, so the flow speed at 2 is the flow speed anywhere along the same pipe. Okay, so we do a rearrangement. So this will be I can group these two together. Okay, so this is half times 50 is 25. 25 plus 1 is 26. 26 C2 square over 2G is equals to 30. Okay, so from here C2 square or C straight away you can calculate to be 4.75 meter per second. Okay, why this is 26? Because this is 25 ma. 25 C2 square over 2G plus 1 C2 square over 2G. So 25 plus 1 is 26 lah. Oh, okay, simple mathematics. So this is your C2. Next, the rate of flow. Okay, rate of flow simple. Okay, so Q will be A2C2, cross-sectional area given by pi over 4, okay, 100 over 1000 square times 4.75. Okay, so with here you can get your 0.0374 meter cube per second. Okay, so for this question, this is how you do it. Okay, now for the last question. Last question, question 4. Okay, is on a siphon. So we have a band here. Okay, water is removed through this siphon. Okay, the whole pipe is 25 mm in diameter. Okay, and the pipe discharges into the atmosphere. Okay, the barometric pressure head is 10.2 meters of water, meaning to say that atmospheric is 10.2 lah of water. Energy losses in the whole pipe is equivalent to the head of 50 c square over 2g. That means the total losses is 50 c square over 2g. Then you know this is not per meter, this is the total one. Okay, so firstly calculate the rate of discharge. Okay, so how do we calculate the rate of discharge? So it's almost the same as just now that question. We need to find out the flow speed first. Okay, so to find out the flow speed, we need to apply the Bernoulli equation. So preferably between 2 points. So maybe here and here. So I label here 1 and 2. So what we'll do here is we'll apply the modified Bernoulli between 1 and 2. Okay, so P1 over rho G plus C1 square over 2G plus Z1 is equals to P2 over rho G plus C2 square over 2G plus Z2 plus the losses. Okay, so same thing, since P1 and P2 is the same, both atmospheric, both exposed to the atmosphere, so they will cancel off. Here is the surface, so C1 will be 0. There's no flow speed there. Okay, and we also can treat here as the datum. So if this is the datum or the reference point, this will be 0. Okay, so the remaining terms are this. So this will be 0 is equals to C2 square over 2G plus Z2. Z2 is the height with respect to the datum. Datum is here, 2 is here. So it is 1.5 plus 3. So it's negative 4.5. Why negative? Because it's under or below the datum. Okay, plus your total head loss will be 50 C square over 2G. Okay, so rearrange, this will be 51 C2 square over 2G is equals to 4.5. Okay, again why 51? Because this is 50, this is 1, so 50 plus 1 is 51. So C2 square will be C2 will be 1.316 meter per second. Not done yet. Okay, we still need to find the discharge, which is Q, which will be A2C2. Okay, so pi over 4, 25 over 1000 square times 1.316. Okay, so from here you can get, in terms of SI unit, 6.459 times 10 to the power minus 4 meters per second. Okay, so this is the discharge. Okay, so after finding the discharge, what else do we need? So after finding the discharge, for part B, okay, Okay, we need the absolute pressure at point B. Okay, so let me label this as 3. Okay, if you want the absolute pressure here, easy, we can just apply the Bernoulli between these 2 points. So apply modified Bernoulli between 1 and 3. Okay, so P1 over rho G plus C1 square over 2G plus Z1 is equals to P2 over rho G plus C2 square over, sorry, C3, yeah, this should be 3, over 2G plus Z3 plus your losses. Okay, so same thing. Okay, is it truly the same thing? Actually no, because why? Today P1 is exposed to the atmosphere, but P3 is the unknown, so we can no longer cancel them because they are not the same. So P1, what is P1 over rho G? P1 over rho G is the head, right, at point 1. So the head is given by 10.2 meters of water. So the whole term here is 10.2. Huh? Okay, this one, it can be 0 because surface, so no flow speed. Z1, same thing, datum can also be 0. So the left hand side is only 10.2. P3 over rho G, leave it there. Okay, C3. So today C3 is the flow speed in the full pipe. So just now we have calculated the flow speed in the full pipe is 1.316. Oh, there's no change in diameter, so the flow speed should remain the same at all points on the pipe. So it's 1.316 over 2G, and here's the square. Z3 today, okay, is the height above the datum, so it's actually this height. Huh? So how do we get this height? Okay, so this height is actually 8.7 minus this part. So what is this part? This part you can get it by 1.5 minus 0.3. So this is 1.2. So 8.7 minus 1.2 will give you the height Z3. So 8.7 minus 1.2. Okay, plus your head loss. Head loss today is the losses over at this portion only. But the 50 C square over 2G is given for the full pipe. So we need to take a ratio. So how do we compute the ratio? Very simple. We just take it based on the length proportion. So this pipe is only 8.7, right? So it's 8.7 over the full length. Full length is 8.7 plus 16.3. So this is your ratio. Okay? So this is your ratio times the total head loss, which is 50, okay, C square, which is 1.316 square over 2G. Okay, can? So this is your proportionate head loss due to the pipe flow from here to here. 8.7 over the full pipe length times the total head loss. Okay, so density here is 1000. So 10.2 is equals to P3. Actually, do we need to put in the density? No, we don't need. Okay, because the question wants the absolute pressure in B in terms of water. Okay, so we can just leave it rho G. Okay, plus 1.316 square over 2 times 9.81 plus 8.7 minus 1.2 is 7.5. Okay, and then this proportionate term here, so it's 8.7 over